Existence of Nash equilibrium. The contents of this lecture are as follows. We begin with Sperner's lemma. In d dimensions, we consider a set of d plus 1 points called vertices. A simplex is the set of all convex combination of the d plus 1 vertices, as shown here. Informally, this is a two-dimensional simplex. It has 3 points because d plus 1 equals 3 when d is 2. And likewise, this is a three-dimensional simplex which contains 4 vertices. A simplical subdivision is a disjoint partition of the simplex into smaller simplices called cells. Informally speaking, this simplex here in 2 dimensions, this which is a triangle, can be subdivided into smaller triangles like this. And although I've shown these triangles as all of the same size, it need not be like that. A labeling is a mapping from the vertices to the indices 1, 2 until d plus 1. So in 2 dimensions, since we have 3 points, instead of assigning them labels 1, 2, and 3, let's assign labels red, green, and blue, R, G, and B. So each of these vertices of the simplical subdivision is assigned a color R, G, or B. A labeling is proper if and only if the vertex of a simplex is labeled using the indexes of only the involved vectors. So in other words, this is R and this is G. The involved vectors are G and R. So this, any point here, any vertex rather here, can only be labeled R or G because the involved vectors are R and G. So consider this large GB edge. These vertices can be only labeled B or G, and likewise for this edge, large triangle's edge, these vertices can be labeled only B and G. This is the big triangle which has R, G, and B labels. So this is a proper labeling. Now notice that in this RG edge, we only have an odd number of smaller RG edges. So consider this large RG edge here. We have 1, 2, 3, which is odd number of smaller RG edges. Now consider this one. This is an RB edge, and we have smaller RB edges. How many of them? 1, 2, 3, 4, and 5, which is again an odd number. And likewise, for this large BG edge, we have 1, 2, 3, 4, and again 5 number of smaller BG edges. So each time it's odd. A cell is complete if its vertices contain all the labels 1 through d plus 1. Informally, an RGB triangle is complete. So this is an RGB triangle. It's complete. This triangle is GGB, so it's not complete. This is complete. This is not complete again because this is R, B, and B, and so forth. And of course, the large triangle is also complete. Sperner's lemma tells us that there is at least one complete cell each of these smaller triangles is a cell, there is at least one complete cell in delta, which is the simplical subdivision. So here we can see there is one small RGB triangle. Here's another one, and in fact there are quite a few of them here. But let's try to formally prove that there is at least one RGB triangle as long as the vertices are labeled and the labeling is proper. That's Sperner's lemma in 2 dimensions. So consider only this large BG edge. Now, all the smaller BG edges are doors, and I have colored these doors using dotted lines. So these are the doors. Okay? Consider this large edge. Since the two vertices at the corners are R and G, all of these inside vertices are labeled R and G. So there is no B. In other words, we don't have any BG door along this edge. Likewise, along this edge, all the inside vertices are labeled either B or R, so there are no G or green vertices here. In other words, we don't have any BG doors here either. But on this edge, we have an odd number of BG edges. So here's what we shall do. We shall begin from the outside of this triangle, and then we will plot a trajectory. Each time we'll cross a door and then enter one of these small triangles, then use another door to enter another triangle, and keep on doing so. We can step outside and get back in, and we can keep doing so until we find that there are no more doors left for us, because we cannot go back. Each door can be used only once. So we keep going like this until at some point we are stuck. Here we are stuck because we entered this BG door, so we used it, and now we don't have any way to exit this triangle. This small triangle, I mean. Now, since we know that there are an odd number of doors connecting the outside with the inside, and we can use each door only once, so if we start from the outside, we will always land up in the interior, the inside of the triangle, because each time you step inside, there is a even number of doors remaining, and so you can get out again if unless there are 0 doors, and each time you're outside, there are an odd number of doors remaining, so you can always get back inside. So, in other words, whenever you are stuck, it has to be in the inside. It has to be some little triangle where you're getting stuck. So this is where you got stuck. This triangle must be an RGB triangle. Why? Because you entered the triangle through a door, a GB door, and since you cannot exit the triangle, the third vertex has to be a R vertex. Therefore, this is an RGB triangle. We could have chosen another trajectory. For instance, we could have used this door as our starting point and then exited this way and then maybe entered through this door and then here, and this is where we get stuck. And again, it's a BGR, RGB triangle. So we just proved Sperner's lemma for 2 dimensions, and using induction, it can be extended to higher dimensions, 3 dimensions, and from 3 dimensions to 4 dimensions, and so on. So here's what we did. We started off with a large triangle and we labeled its 3 corners using R, G, and B. All 3 must be different. And then we labeled all the uh, vertices uh, along the edges using only the 2 extreme colors, R and G, for all these vertices. Likewise, this is R and this is B, so all these inside vertices we used only R and B, and likewise for R and G. And the inside vertices we are allowed to use any arbitrary color. Then we showed that if this is the way we labeled all our vertices, there must be a small RGB triangle. That's Sperner's lemma in 2 dimensions. Next, we begin with Brouwer's fixed point theorem. Suppose D is a compact set and F is a continuous function that maps D onto itself. It's a continuous function and it maps D onto itself. Then the function f has at least one point x naught in D such that f of x naught equals x naught. Since it's a mapping from D onto itself, so f of x naught equals x naught is plausible, and in fact there exists at least one such fixed point, fx naught equals x naught. Informally, D is this 2-dimensional surface of this cup of coffee. And by applying this function f, we are stirring this coffee. And this function must be continuous. In other words, we cannot take a spoonful of coffee from here and put it here, because that would introduce a discontinuity in the function. The function has to be continuous. So according to Brouwer's fixed point theorem, we know that all the points in the surface are displaced, but there is at least one point here whose position remains unchanged. So that is the fixed point. F of x naught equals x naught. Homeomorphism. Sets A and B are homeomorphic if there exists a continuous bijective function h mapping A to B such that h inverse, the inverse function, is also continuous. Now it's a fact that the compact set D is homeomorphic to a simplex. Informally, it means that this surface of this cup of coffee is homeomorphic with this triangle. Remember the triangle from Sperner's lemma. Using Sperner's lemma, it can be shown that delta has a fixed point. Now, instead of stirring the coffee, we will assume that we stirred this triangle because our surface was homeomorphic to this triangle. Now let's ignore the labeling at this point. We'll see it's labeled in a particular way. Now each vertex, as a result of the stirring, gets displaced in some direction. So you see this vertex here, this moves here, this vertex here moves here, this vertex here moves this way, and so on. So we mark the directions of motion with a arrow each. And the vertices, except the three outer vertices G, R, and B, uh, the other vertices are labeled based on the direction of the arrows, as we shall now see. Now, these vertices are getting displaced in the direction of this edge. So it's the GB edge. So we color these vertices red, not G or B. These vertices are moving towards the RB edge, and so they are colored green. And these vertices are moving towards the GR edge, and therefore they are colored blue. You can color the vertices using the label that's not involved in the edge. Now from here, it can be easily seen that the labeling of the vertices on the edges of this triangle are proper, because any point here on this edge cannot move in any direction other than towards either GB or RB, and so it can only be colored green or red. Likewise, any uh, vertex on this edge, RB edge, can only be colored B or R. B if it's moving along the towards the RG edge, and red if it's moving towards the BG edge. It cannot be ever colored green because it cannot move in this direction. It cannot move away from the edge. So the conclusion is this labeling is proper. And now we can kick in Sperner's lemma. There exists a small RGB triangle, at least one. And this RGB triangle is not displaced. It can get squished or it can turn a little bit, but it's not moving in any one direction. Unlike, say, this triangle is clearly moving this direction, and so is this triangle. This triangle is moving towards somewhere in this direction, maybe. Combination of blue and green, but this RGB triangle is not getting displaced. Likewise, this RGB triangle is not getting displaced, and in fact, it is getting compressed a little bit. So this is a fixed point that is not getting displaced. And if this is not convincing, we can again uh, partition this small RGB triangle, or pick any small RGB triangle, and partition them into even smaller triangles, and then apply Sperner's lemma and keep continuing the process till we get infinitesimal RGB triangles, and so there is at least one RGB triangle, uh, infinitesimal RGB triangle, which is a point that is not getting displaced but when we stir our triangle. Therefore, this is a proof of Sperner's lemma. Thus, there exists some infinitesimal RGB triangle that's not displaced by application of stirring, which is uh, due to the application of the function f of x at each point x. So we have informally proved Brouwer's fixed point theorem. Now let's restate Brouwer's fixed point theorem uh, before we proceed further. So if D is a compact set and F is a mapping from D onto D, then there exists at least one fixed point x naught of D such that f of x naught equals x naught. And D was homeomorphic to a triangle in 2 dimensions. We shall specifically use this fixed point theorem to show that a Nash equilibrium will exist for any game. And in fact, this fixed point will be the Nash equilibrium point. So our goal is to create some function which maps a strategy onto another strategy, some function f. And this would be the probability space of all joint strategies. Before we begin with the proof, let's first construct this function gi ai si s negative I. So what is this function gi? First of all, gi is unique to agent I, so we'll have to construct this function for every agent I. What are the arguments of this function? A pure action of agent I and a mixed joint strategy. So this mixed joint strategy consists of a strategy, a probability distribution over actions of agent I and likewise for its opposing agents. So this is a complete joint strategy. And this is a pure action of agent I. So we define this function g sub I of this as this. Maximum of 0, comma, this difference here. And this difference is the payoff of agent I when it's playing the pure action AI, and this is the payoff when it's playing the strategy SI. Note that the opponents play the same joint strategy S sub I in both cases. And what does this maximum do here? This maximum simply thresholds this difference at 0. So this function can never be negative. So let's look at the payoffs of agent I in both cases. The opponents are playing the same mixed strategy S sub negative I in both cases. Now, this is the difference between the two payoffs. Here, it's the payoff of agent I when it's paying the pure action AI, which is the first argument here. And here, it's playing the mixed strategy S sub I, the second argument here. And this difference, suppose AI, this pure action, fetches a higher payoff for agent I than this mixed strategy, then this difference is positive. And so this thresholding max 0 comma difference doesn't make any changes. So what this function uh, yields is the difference between the payoffs, which is positive because action AI is better, yields a higher payoff for the same agent than the mixed strategy S sub I. Now, on the other hand, if the pure action AI is not better than the mixed strategy SI for that agent's payoff, then this would be higher than this. So this here would be difference here would be negative, and we are thresholding it to 0. So the function will give a value of 0. So the function gives a value of some positive value, which tells us by how much this pure action is better than the mixed strategy for agent I, and otherwise, if it's not better than Si, then Gi becomes equal to 0. And we know that at Nash equilibrium, no pure action can yield a higher payoff for the same agent than the Nash equilibrium strategy. So at Nash equilibrium, Gi Ai comma S star equals 0. So let's take up this example of rock, paper, scissors. Now, agent 2 is playing rock and paper with equal probability, and he's not playing scissors. Agent 1 here plays the Nash equilibrium strategy, which is randomizing over R, P, and S with equal probabilities. Now, the payoff of agent 1, we are looking at agent 1, okay? The payoff of agent 1 for this mixed strategy of agent 1 and this mixed strategy of agent 2 is this, which is equal to 0. This is the payoff P1, which is taken by taking the first elements of each box here. 0, negative 1, 1, 1, 0, negative 1, and so on. 0, negative 1, 1, 1, 0, negative 1. And so this payoff for these joint strategies is 0. Now let's consider action A1 equals paper. Suppose instead of playing this mixed strategy, agent 1 decides to play paper only. Then let's see what happens. So the action is 0, 1, 0, and pi 1, the payoff is 0, 1, 0 times P1, the payoff matrix, times S2. S2 remains the same. The opponent of agent 1 is not changing its strategy. So the payoff in this case, if you do the multiplication, it turns out to be 0.5. 0.5 minus 0 is 0.5. It's greater than 0, so we don't have to threshold it by this max. So G1 P comma S1 S2 equals 0.5. Let's consider another action R for the same agent, 1, 0, 0. In this case, now remember that the opponent is playing rock and paper with equal probability and not playing S. It's this strategy here. Now, what's the payoff of agent 1 if he plays red only? Common sense tells you that if the opponent is playing rock and paper, if you play rock, excuse me, I said red instead of rock, then it will lose half the time when the opponent plays a paper, and it will be a tie half the time. And so here, pi1 r comma s2 is negative 0.5, because agent 1 will lose half the time and it will be a tie half the time. Therefore, now this is negative, so this minus this is negative, and so we have to threshold the difference. When we take the difference between negative 0.5 and 0 and apply the threshold, the max, we get a 0, because negative is not allowed for the function g, so we get a 0 here. Similarly, if a1 equals s, then we would get a 0. Because in that case, if agent 1 plays scissors and agent 2 plays rock and paper, half the time he will lose and half the time he will win. And so the expected payoff in that case is 0. Therefore, you take the difference between 0 and 0, that's 0. So G1 equals 0. So here are the three values of G1 for each action of the agent 1, R, P, and S. In fact, what do these values tell us? That playing paper is good, right? Because it has a positive value here. But playing rock and paper are not so good. In other words, instead of playing this S1, if we nudge this strategy, mixed strategy, towards paper, then maybe it'll yield a slightly higher payoff. So let's see. So this is our S1. To this S1, we add the three G1s. G1 for rock, G1 for paper, and G1 for scissors, which is 0, 0.50, and we get this. Maybe moving S1 to this will yield a higher payoff, because as you can see, paper gives you a higher payoff. Unfortunately, this is not normalized. If you add up all these three, you don't get 1, you get something more than 1. It's 1.5 actually. So we need to normalize. So this is S1 prime, which is this. And it's a strategy because we have normalized. The sum of the probabilities will now add up to 1. And this S1 prime would yield a better payoff than the original S1. On the other hand, if the opponent, agent 2, were playing Nash equilibrium and so was the agent 1, then the values of G1 would be zeros for each of the pure actions R, P, S. And so there's no need to move away from the Nash equilibrium strategy in this case, because agent 2 is also playing the Nash equilibrium strategy. So when S1 equals S1 star, then when we do that little moving, nudging S1 along the direction for better payoff, we simply get S1 prime equals S1 star, which is 1/3, 1/3, and 1/3. So at Nash equilibrium, it's not possible to push the strategy along any direction. Next, let's define this function f, which is a mapping from the joint strategy space to the joint strategy space. S prime I of action I equals probability of action I in Si plus this Gi of action AI. And this is in the numerator. In the denominator, we have 1 plus summation over all actions of GI for each of these actions. Now, since I've used AI here, it's part of the argument, so I'm doing the summation over BIs. Note the slight notation change. In our little example earlier, we had agent 1 was I and agent 2 was negative I, and these were the strategies. And so if we apply this expression to agent I, for each action R, P, and S, we had evaluated the values of GI, which was G1, and we got 0, and for P we got 0.5, and we got 0 for S. Rock and scissors gave us zeros, and GI for P was equal to 0.5. So let's look at the denominator of this. The denominator is equal to 1 plus summation over all actions. So 1 plus GI for R plus GI plus for P plus GI for S, which is 1, plus 0 plus 0.5 plus 0, which is 1.5. And so this S prime I for R is equal to this numerator. This is 0.33. P of AI given SI is 0.33. Rock is being played with a probability of 0.33 in SI. And so this is 0.33. And GI for rock was 0. So we put a 0 here. This is action AI is rock now. We put a 0 here. And the denominator is 1.5. The denominator is common to all three actions. And the numerator for paper is 0.33 because this 0.33 was the probability in SI of paper being played. And then GI for paper is 0.5, so we put a 0.5 here. Denominator is 1.5, and likewise we compute S prime I for S, the third strategy, third action, excuse me. And so this is the vector S prime I. This is the new strategy, and we already saw that this new strategy S prime I nudges SI along a direction where agent I would get higher payoff. And likewise, for the other agent, we do the same math. We swap I with negative I, and so these are our strategies, and then we find S prime of negative I. And therefore, this function f s I s negative I is equal to this. It's a mapping from the joint strategies to the joint strategies. So here f of s1 equals 0.33, 0.33, 0.33, and s2 equals 0.5, 0.51 gave us s prime 1, which was equal to this, which we had seen in the previous slide. And likewise, after we compute S prime 2, plug in the value here. So this is how we evaluate the function f. Now observe that f is a mapping from the strategy space of agent 1 cross strategy space of agent 2 into, again, strategy space of agent 1 cross strategy space of agent 2. And each strategy space is a subset of 0, 1 to the AI. A1 is RPS, so this is 3. So this S1 is a subset of 0, 1 to cubed, and S2 is also the same here. It's the interval 0, 1 cubed. But note that so each of these is a three-dimensional vector, but the sum of elements must add up to 1 because they're probabilities. That's why it's a proper subset. And if you remember Brouwer's fixed point theorem, it was a mapping. We were considering a continuous mapping from compact set D to a compact set D. So in this case, the mapping is from S1 cross S2 to S1 cross S2, and that's our compact set, S1 cross S2. And therefore, there will be a fixed point in S1 cross S2. So now let's go ahead and prove formally that every game has a Nash equilibrium. Our proof will be in 3 steps, 1, 2, and 3. In the first step, we will show that S prime I for each agent I, S prime I of AI, we sum S prime I over all possible actions of agent I, and this gives us 1. So, in other words, S prime I is a vector, and the sum of its elements equals 1, which would indicate that S prime I is a valid strategy for agent I. In the next step, we show that if any action AI of agent I is better than the agent's mixed strategy, Si, then probability of AI is more in S prime I than it is in Si. But if this action is not better than Si, then the probability of that pure action in S prime I is less than equal to the probability of that action in Si. In other words, S prime I is no worse than S prime for agent I. Agent I would not receive a payoff that's lower than Si when it plays S prime I. And lastly, in the third step, we invoke Brouwer's fixed point theorem. There exists a fixed point of this function f such that f s star equals s star, and that fixed point is in fact the Nash equilibrium. We proceed with the first step of the proof. Now, S prime I is a vector, and the sum of the elements of that vector for all actions AI should equal to 1. And that means that S prime I is a valid strategy for agent I. So we start with the summation of the numerator, this here, with BI in place of AI. So this summation of the numerator is equal to summation of this here, probability of BI given SI plus GI of AI SI S negative I. So this, and then I break up the two terms. So the first summation is summation over all actions of agent I of P of BI given SI plus summation of GI of BI SI S negative I. Now we know that SI is a valid strategy for agent I. Therefore, its sum of the elements should equal 1. So we have a 1 here. Sum of the probabilities of picking each action is equal to 1. And this is the second term, this summation here. And so this, if you compare this with the denominator, they're the same. So summation of the numerator equals denominator, and therefore this shows that summation of S prime I over all actions is equal to 1, so that S prime I is a valid strategy for agent I. Step 2 of our proof, we have to show that S prime I is no worse than Si for each agent I. First, note the notation. S prime is a vector, and its element corresponding to any action AI is the probability of that action. And since we showed that S prime I is also a mixed strategy, its element corresponding to any action AI is also the probability of that action in S prime I. So this is the expression for S prime I of AI. I just copied it from here, and P of AI given Si is nothing but the element of Si vector corresponding to the action AI. Now let's look at what happens. Suppose AI, this action AI is better than Si. It yields a higher payoff for the agent I. Then what happens? GI is the payoff with the pure action AI minus the payoff with the mixed strategy Si. And if this payoff is higher, then GI would be a positive quantity. So if AI is better than Si, then this GI here, GI will be greater than 0. And therefore, this S prime I of AI will be more than S prime of AI. So this would be more than Si of Si, sorry about this, Si of AI. On the other hand, when AI is not better than Si, the payoff with agent I playing AI is not any better than when it's playing Si. In that case, what happens? This difference would be negative or 0, so that GI would be 0. In other words, there would be no increment in SIAI. The probability, because of the normalization, the probability might decrease, but it cannot increase. So, if AI is not better than Si, then probability of AI in S prime I is always less than equal to the probability of the same action in the original mixed strategy Si. Thus, S prime I biases Si towards actions with better payoffs. That's part 2 of our proof. Before proceeding with the last and third step, let's recall Brouwer's fixed point theorem. Here we have a compact set D whose number of dimensions is equal to the cardinality of the joint action space, which is the product of the cardinality of the action spaces of each agent. And we consider a continuous function from D to itself, then this function has at least one fixed point S star in D, such that f of S star equals S star. So that's the Brouwer's fixed point theorem. And this mapping f from D onto itself informally is like stirring the cup of coffee without introducing any discontinuities in it. And what the fixed point theorem says is there will be some fixed point here in this surface of the coffee which will not change position as a result of the stirring. So now let's begin the third step of our proof. We have to invoke Brouwer's fixed point theorem. And then it will show that f of S star equals S star. There exists such a point. Now, from the principle of indifference, suppose AI and BI are two pure actions that are in the support of S star I, the Nash equilibrium strategy of agent I, then both actions which are in its support yield the same payoff. Pi I with AI is equal to pi I with BI. The opponent agents are playing the Nash equilibrium joint strategy. On the other hand, suppose AI lies in the support of S star I, but BI does not lie in the support of S star I. Then it necessarily means, from the definition of Nash equilibrium, that the payoff with AI will be greater than the payoff with BI, which is not in the support. This is for strict NE, and it will be greater than equal to in case of just a Nash equilibrium. Whence, at Nash equilibrium, f of S star I, S star negative I, will give you S star I, S star negative I, because no pure action will yield a higher payoff. Or since S star I, S star negative I is the joint strategy of all agents, we say S star equals S star. Now, invoking the Brouwer's fixed point theorem, we know that f has at least one fixed point such that fs star equals S star. This here. And this S star, the fixed point, is the Nash equilibrium of the game. In other words, we have just proved that every game has a Nash equilibrium.